Hi everyone, welcome to Writing and Naming Binary Ionic Compounds. Up to this point, you have looked at how to write and name just the cations and anions. Today what we're going to do is learn how to write and name them as a compound. In the previous section, you used the three-step method in order to do those. Now we're going to show you a shortcut. Kind of like in math, when you learn the long way how to do something, there's always a shortcut. So what does that word binary mean? The only compounds we're going to learn how to do today are those composed of only two elements, which means you're going to have one cation and one anion. Remember, ionic compounds are made up of metals and nonmetals. You have the cation, which is the metal, a positive ion, always written first. And then you have the anion, which is the nonmetal, the negative ion, always written second. Overall, please keep in mind that we need to create a formula unit that is neutral. Some examples of these might be beryllium phosphide. Could you write that formula? How about the formula for cesium oxide? How about the formula for chromium 3 iodide? How would you name Li2O? How would you name CaF2? By the end of this video, you should be able to write the formulas for any name that I give you for a binary ionic compound or name from a formula. Let's start with an example between aluminum and oxygen. The first thing we're going to do is write out the ions. Now this part is all scratch work. Some of you will get to the point where you might not need the scratch work. Some of you are always going to need scratch work, so having scratch paper handy is always to your advantage. So we're going to write the ions. You have ion sheets that were available to you on Schoology, or you can use your periodic table. Aluminum is group 13, so it's going to have a +3 ion. Oxygen is group 16, it's going to have a -2 ion. So we wrote the ions next to each other. We're not writing a formula yet. This is all scratch work. Now what we're going to do is forget about the plus and minus. Don't worry about those. We're not going to deal with those. Pretend they're not even there. Now these red lines represent where we're going to put subscripts. We know that in the chemical formula, we need subscripts to represent the number of atoms in it. In an ionic formula, these subscripts are going to represent the ratio of the atoms in the crystal. So we're going to write subscripts on those red lines. How do we know what subscripts to put on those red lines? Well, what we're going to do is switch and drop those numbers. So the 2 and the 3 will be switched and dropped onto the lines. So the 2 goes next to the aluminum, and now the 3 goes next to the oxygen. Since we know that in an ionic crystal, the formula unit, or the chemical formula, represents the ratio of the atoms in the crystal, we need to see if we can reduce that. Does a 2 and a 3 reduce? No, it does not. And you can only reduce what we wrote on those red lines. So this does not need reduced. So now we're ready to write the formula for the crystal that involves aluminum and oxygen. No charges though. So we take the aluminum with the subscript 2, the oxygen with the subscript 3, and we have our formula. Now we need to name it. When we name cations, which would be the positive ions, our metals, we need to take into consideration as to whether or not that metal needs a Roman numeral. Some metals have more than one form of their ion. So let's take a look at the periodic table. Let's find aluminum. Does aluminum need a Roman numeral? The ones that need Roman numerals would be more in this section down here, in the lower P block and the D block. Is aluminum in that section? It is not. which means that aluminum does not need a Roman numeral. So if it does not need a Roman numeral, we can just name that cation. Remember, though, there are a few within that D block that also do not need Roman numerals. Gallium and indium are not in the D block, but they're in the lower P block. They don't need them either. So aluminum is not any of those that need a Roman numeral. So we can just name it as its cation, which would be aluminum. To name the anion, all we do with the oxygen is drop the ending and add an "ide." So this compound is called aluminum oxide. The formula is Al2O3. It's called aluminum oxide. Our next example is between zinc and iodine. We're going to write the ions again. You can use your ion sheets to figure out that zinc has a +2 charge and iodine has a -1 charge. Remember, forget about those charges themselves. And if we don't have anything next to a minus or a plus, it's understood to be 1. So, we know we're going to write our subscripts on these red lines. We're going to switch the superscripts and drop them. So the 2 is going to come down here. What's understood to be the 1 on the iodine will come down here. I'm going to write the 1 in, but we're not going to write in our final formula. So we also need to consider, does this need reduced or not? Well, we can only reduce what we wrote down on those red lines. You can add that to your scratch book if you want, if it helps. Does this need reduced? Does a 1 and a 2 get reduced? No, it does not. So we're going to write our formula now. Ignore this, no charges, just neutral, no superscripts. So Zn with a subscript 1, which we do not write, and iodine with a 2 subscript. Now we need to name it. Zinc is our cation. Does zinc deserve a Roman numeral? Let's look at the periodic table. Now here is zinc. Yes, zinc is on our D/lower P block. However, keep in mind, there are a few in that area that do not deserve Roman numerals because they only have one form. And look at that. Zinc is one of them, so zinc does not get a Roman numeral. So zinc is just simply zinc. And then we will do the same thing with our anion as we did in the last example. We'll drop the ending and add an "ide." So iodine becomes iodide. So here we have ZnI2 as zinc iodide. Our next example is calcium and bromine. We're going to write our ions down. A Ca+2, a Br-1, calcium's in group 2, which has a +2. Bromine is our anion in group 17, which has a -1. It has 7 valence electrons, which means it's going to gain 1 and become more negative. So we're going to figure out what is the ratio in the crystal between the calcium and the bromine. Remember, we don't need to worry about those charges. And if there's no number next to the plus or the minus, that means it's a 1. We can think about 1s as we're doing our scratch work, but we do not write 1s in the actual chemical formula. So we're going to put something down here to remind us that this is the only place we can reduce what we drop on those lines. So we can switch and drop. The bromine has a -1 charge. The calcium has a +2. So the 2 is going to come now down next to the bromine, and the 1 will come down next to the calcium. Again, we can see the 1 right now in our scratch work, but we're not going to put that in our final formula. What we need to do next is start the naming of our cation after we reduce. Can we reduce a 1 and a 2? No, we cannot. So we don't need to worry about reducing right now. So let's go on to writing the formula. So we have 1 calcium and 2 bromines. Again, we do not write the 1. So it's a CaBr2, which is a ratio of 1 calcium to 2 bromines in the crystal lattice for this particular ionic compound. When we name it, we need to look at the metal, which is the calcium. doesn't need a Roman numeral. Let's look at the periodic table again. Where is calcium located? Calcium is way over to the left in group 2. Is it part of our D block? Lower P block? No, it's an alkaline earth metal. It does not need a Roman numeral, so we don't have to worry about that. We can just simply name it as its metal, which is calcium. And then again, for our anion, we're going to drop the ending and add the "ide," which bromine would become bromide. So CaBr2 is calcium bromide. Now let's look at the compound that forms between lead 2. Now that Roman numeral means that is the charge we're going to be using for the lead, because lead does have multiple forms of ions that it can form. So we need to look at the Roman numeral to determine what charge is going to be in our compound. So in this case, when we write the ions, the lead is going to have a +2 charge. The oxygen, no different than any other time, it's still in group 16, which is a -2 charge. Remember, forget about those little pluses and minuses for now. And we're going to switch and drop very soon, and something's going to go onto those lines. Remember, those red lines are the only ones that you can reduce. So let's switch and drop. So the 2 from the lead is going to come down next to the oxygen, and the 2 from the oxygen is going to come down next to the lead. Look at what's on the red lines. Can that be reduced? Absolutely, it's a 2 and a 2. So we're going to reduce that down to a 1 and a 1. Please keep in mind that we do not write 1s in our final formula. When we write our final formula, you will have 1 lead and 1 oxygen, but you will not have 1 as a subscript. Now let's name it. Lead is our cation. Does lead need a Roman numeral? Again, let's refer to the periodic table. Lead is down in the lower P block. And it looks like lead does need a Roman numeral because it's not one of our 3, or gallium and indium, that don't need it. So we're going to give it a Roman numeral. So the Roman numeral pertains to the original charge on the lead. The original charge on the lead. So that original charge was a +2. So it's going to be called lead 2. And again, for our anion, we're going to drop the ending and add an "ide. And that will be oxide. Now let's look to see what happens with lead 4. Very similar situation. We have lead 4 and oxygen. Again, forget about those charges. And we're going to drop our subscripts. And if needed, reduce. Let's see what happens when we switch and drop. The 4 comes over to the oxygen. The 2 comes over to the lead. And can we reduce those? A 2 and a 4? Absolutely, that can be reduced down to a 1 and a 2. We already know, due to lead's location, that it will need a Roman numeral. But let's write the formula first. Lead has, in the ratio, it's going to be 1 lead to every 2 oxygen. You do not write the 1s in the final formula. Again, we know that lead will need a Roman numeral due to its location on the periodic table. It's in the lower P block, and it's not one of our ones that does not get a Roman numeral, so yes, it needs one. So it will be lead 4, always going back to the original charge on the cation. And then for the oxygen, we're going to drop the ending and add that "ide." Another example is iron 3 and nitrogen. Iron 3, that 3 means that the charge on the iron is a +3. Nitrogen is in group 15, which means it has 5 valence electrons. It needs 3 more, so it's going to have a -3 charge. Remember, forget about those charges. They don't even exist right now. And then we're going to drop something on to our lines. Our scratch work, this is our scratch work, folks. So a 3 comes down next to nitrogen, and a 3 comes down next to the iron. Can we reduce that? A 3 and a 3? Absolutely. It's going to get reduced down to a 1 and a 1. So the ratio between the iron 3 and the nitrogen in the crystal is going to be a 1-to-1 ratio, so the formula is Fen. Now, when we go to name that, we need to take into account what the charge was originally on the cation. Iron is located in that section. It is not one of our 3, or gallium or indium, so it does need a Roman numeral. We already know what charge it had, so we can name it appropriately based off of the Roman numeral that we know it had, which is the 3, so it's iron 3. And then for the anion, we're going to drop the ending and add the "ide", so it's nitride. Okay, now a little different. The next 3 examples are going to be the reverse of this, taking a formula and coming up with a name for it. Again, when you're looking at the cation, you need to take into consideration, does the cation deserve a Roman numeral or not? In this case, does copper need a Roman numeral? We'd have to know if this formula was reduced. Right now we're looking at a ratio of 3 coppers to 2 phosphorus, Cu3P2. Was this reduced or not? And that's going to help us to name copper's cation properly. So let's look at what we need to do. We're going to name the cation. Find copper. Is copper in our section that needs a Roman numeral? It is. And it's not one of our 3 here, and it's not gallium and indium. So copper will need a Roman numeral, absolutely. So let's leave some space for the Roman numeral. We don't know it yet, but let's just leave some space for it. And let's name our anion. P is our anion. P is phosphorus. So what do? We drop the ending and add an "ide", so it's going to be called phosphide. So we know it's copper something phosphide. At this point now, we need to figure out what was the original charge on the phosphorus and was this reduced or not. So currently right now we're seeing a 3-to-2 ratio between the copper and the phosphorus. Was that reduced or not? Look at the original charge on the phosphorus. The original charge on the phosphorus was a -3. If that's the case, then I should see a 3 next to the copper if I switched and dropped. And I do see a 3. So was this reduced? If the original charge on the phosphorus was a -3, you can even look that up on your charts, or you know it's in group 15, it has 5 valence, it gains 3, which is a -3. If phosphorus originally was a -3, and we see a 3 next to the copper, was this reduced? And the answer is no. It was not reduced. If the original charge on the phosphorus was a -3 and we see a 3 next to the copper, it was not reduced. So all we need to do now is take a look at what was on the next to the copper, reverse that back up, and know that our original charge on the copper was a +2, which makes this copper 2. So our final name for this formula is copper 2 phosphide. The next 2 are a little bit more complicated. We have SNO. We know it's tin something and oxygen. Does tin deserve a Roman numeral? Locate tin. Tin is number 50, and it is in our section that deserves a Roman numeral. It is not one of our 3, and it's not gallium or indium, so yes, it does deserve a Roman numeral. So let's start with writing tin down and a space to write the Roman numeral. We're not going to figure out the Roman numeral yet. The anion, drop the ending and add the "ide". Oxygen, dropping the ending and add an "ide" is oxide. We're still not done yet. We need to figure out, we know something, we need to figure out the Roman numeral for the tin. Tin has many forms. So let's figure out whether this was reduced or not. By the way, even if it's not on your ion sheet, you can have charges that go up to +7. Just keep that in mind. You have to be able to figure that out. So in this case, right now, the ratio between the tin and the oxygen is a 1-to-1 ratio. Folks, keep in mind, we already know that the original charge on the oxygen, group 16, is a -2 charge. So if that's the case and we switched and dropped, what should we see next to the tin? Shouldn't we see a 2? I don't see the 2. So if I don't see the 2 next to the tin, what does that mean? Was it reduced? Yes, it was reduced. So now we need to figure out what the original ratio was. So if this should be a 2, since the original charge on the oxygen was a 2, then what was the original charge on the tin? So right now, there's a couple ways you can do this. You can look at the original, the ratio between the tin and the oxygen. Currently, right now, is a 1-to-1. We know that should be a 2. So what's a 1-to-1 equivalent? What's equivalent to a 1-to-1? A 2 to 2. So if you reduce the 2 to 2, you end up with 1-to-1, which means that the original charge on the tin was a +2. Mathematically, there's a different way you can do this. You can approach it as, you know that the original charge on the tin was a -2. The ratio between the tin and the oxygen is 1-to-1. So you have 1 oxygen at a -2. What's going to neutralize that if you have 1 tin at a blank? What's it going to have to be? Well, to have a -2 times 1, what's going to be neutral? You're going to have to have a +2 times 1 to equal neutral. So either way, it's going to turn out to be that the name of this compound is tin 2 oxide. The last example for today is SnO2. We just did tin, and we already know it needs a Roman numeral because it is in the lower P block. It's not one of our little losers, and it's not gallium or indium. So absolutely, it deserves a Roman numeral. It has more than one form of its ion. So we need to figure out what that is. And then oxygen, we drop the ending and add the "ide," and that's going to be an oxide. So let's figure out what was the original charge on this. Was it reduced or not? So currently, right now, between the tin and the oxygen, I'm seeing a 1-to-2 ratio. What was the original charge on the oxygen? Well, we know already it's a -2. It's group 16. It gained 2 electrons. So if that's the case, what I should see next to the tin is a 2. And I don't see a 2, I see a 1. So was this reduced? Absolutely, it was reduced. Currently, right now, I'm seeing a 1-to-2 ratio. What does that equate to? I'm seeing a 1-to-2 ratio instead of a 2 to what? What's equivalent? 1 to 2 equals a 2 to 4. So the original charge on the tin was a 4. So that makes this tin 4. Another way you can look at it is mathematically, knowing that your ratio between the tin and the oxygen is a 1-to-2, and that the original charge on the oxygen is a -2. What would 1 have to be multiplied by in order to reach a -4? Well, it would have to be a +4. So that again makes this a tin 4 oxide. So at this point, I want you to freeze your video and practice the following. For numbers 1, 2, and 3, I want you to write out the formulas for them. And then for 4, 5, and 6, name them. You can put those on the inside cover of your note packet or calendar packet. I will put answers on Schoology later today, and I will ask you to screenshot me your answers and submit them to me and let me know how you did. All right, everyone, thanks and have a good day.